Alright, on this problem we're going to be working the solubility product. So the first thing we do in pure water is we set up our equation, and it's barium 3 arsenate. Now we want to leave room. This is a solid, and it's going to dissociate into 3 barium ions plus 2 arsenate ions. So again, these are both aqueous, so we're going to set up our ICE table. So it's going to be 1, 0, 0, minus x, plus 3x, plus 2x, 1, 3x, 2x. Now this one's a lot more complicated than most of them. So when we do our KSP, it's going to be equal to the barium ion raised to the 3rd power times the arsenate ion raised to the 2nd power. So it's 1.1 times 10 to the minus 13th is equal to 3x cubed times 2x squared, which is equal to 27x cubed times 4x squared, which means 1.1 times 10 to the minus 13th is going to be equal to 108x to the 5th. So x to the 5th is equal to 1.0185185 times 10 to the minus 15th, raise it to the 1/5 power, or take the 5th root, whichever your calculator and you can get along with, and you're left with 0.001003676, which is, if we report it 4 decimal places, it's going to be 0.001004 molar. Now, this is the solubility of the barium arsenate. It's the X value. So we're going to move on to the next one, where we will have added a common ion. So again, we'll set up our ICE table. The solid concentration is still 1, but now our barium is still 0, but now we have the arsenate, and it's 0.15. So minus x, still 1, plus 3x, 3x in the end, minus plus 2x is 0.15 plus 2x. Alright, so what we've got here is your KSP is 1.1 times 10 to the minus 13th is equal to 3x to the 3rd times 0.15 plus 2x. Now at this point, this one's squared. You don't want to do the math. So we're going to assume that 2x is much, much, much less than 0.15, which, looking at the value previously, which is 0.001, it's not going to be bigger than that, so it's going to be much less. So we're going to get 1.1 times 10 to the minus 13th is equal to 27x cubed times 0.15 squared, which is equal to 0.6075 x to the 3rd. So x to the 3rd is equal to 1.8107 times 10 to the minus 13th. Okay, which is much less. So we got to do x is equal to 5.6574 times 10 to the minus 5th, which again is much less than what we had before, because we were 10 to the minus 3, now we're 10 to the minus 4. We still have to check it. So what we're going to do is 2 times 5.6574 times 10 to the minus 5th, because we assumed that 2x was greater than 0.15 divided by 0.15 times 100 is equal to a whopping 0.07543%. Therefore, my assumption is valid. Okay? So that brings us to the third problem, which is where we have the common ion of the barium. So again, we're going to set up our IC table. So it's 1, except on this time we have 0.15 at the barium and then 0. So it's minus x, still 1, plus 3x plus 2x, and it's 0.15 plus 3x and 2x. So running out of room here, so I'm going to work over here. So again, our KSP, which is 1.1 times 10 to the minus 13th, is going to be equal to 0.15 plus 3x to the third times 2x squared. Okay? So this value is going to even be worse than squaring it, so we're going to assume that 3x is much less than 0.15, which brings us to the value of 1.1 times 10 to the minus 13th is equal to 0.15 cubed 2x squared, which is equal to a whopping 0.0135 x squared. So if we do the math here, then x squared comes out equal to 8.14815 times 10 to the minus 12th, which x is equal to 2.8545 times 10 to the minus 6th. Now, if you notice, it's even smaller than the previous one. But we made the assumption, so we're going to have to do the check. So 3 times 2.8545 times 10 to the minus 6th divided by 0.15 times 100 is even smaller, 0.005709%. So our assumption is valid on this one. So we're done with the solubility product problem.